Sass class with Amanda. Hey. So in this video, we're going to learn about tree diagrams, which is a method of keeping track of probabilities, especially when there are multiple experiments happening. So for example, if we're tossing a coin 3 times, we can calculate various probabilities the way we used to, or we can use a tree diagram. So we flip a coin once. We get either heads or tails. Okay, so each branch has to be disjoint of the other. And every time this has to add up to, each branch has to add up to 1. So this is 1/2. Probability of getting tails is 1/2. We flip a coin again, either we get heads or we get tails. Okay, again, the probability is 1/2, probability is 1/2. And we do it one more time because we can flip a coin one more time. Heads, tails, again 1/2, again 1/2. Right? But we have to fill out the rest of the branches because every path is a legitimate path. Each one has an equal chance of occurring. So here we have to do that all over again. This might seem a little mundane when it comes to flipping a coin, but it's a nice easy example to understand how to create a tree diagram. Alright, so this adds to 1, this adds to 1, this adds to 1, this adds to 1, this adds to 1. Okay, so every experiment has to add up to 1. Alright, but now what happens when I want to calculate the probability of flipping a coin and getting a tails on the first flip, then a heads, then a tails, right? And so there's only one outcome here. It's tails, heads, tails. And how do I calculate that probability? Well, this has no influence over that, which has no influence over that, and this occurrence is the intersection of all 3 flips, right? This event is the intersection. So this is the probability of tails times the probability of heads times the probability of tails, which is equal to 1/2 times 1/2 times 1/2, which is 1/8, right? So several things to note again is that each, I guess I'll call it level, add to 1, or sum, sorry, sum is probably a better word, sum to 1, and that's all the branches, okay, so for example this, for example that, etc. And also the probability at lower levels is the assigned probability for the event times all parent branches. That is, if we're talking about tails, tails, tails. Not this individual tails, but the event tails, tails, tails. Right? If I was just flipping a coin twice and I wanted the event tails, heads, then it's 1/2 times 1/2 only. Let's look at a little bit more interesting problem where there's lots of things happening. The world is being laid to waste by zombies. As one of the last human survivors, you have an 82% chance of being bitten by a zombie. 95% of people bitten become zombies, and 5% of people bitten survive by amputation. Of the people who survive by amputation, they die by human hands 95% of the time, 3% by hunger, and 2% by thirst. If you don't get bitten, you can survive. But you have a 45% chance of dying from hunger, 15% chance of dying from thirst, and 40% chance of dying by human hands. What is the probability that you die from thirst? Alright, so we want to pay attention to all the different outcomes that can happen, right? So first, starting out during the apocalypse, you're human, you're fine, but then, you know, zombies come out and either you get bitten or you don't get bitten, right? So either you're a human being that is bitten or you're a human being that does not get bitten. And we're told that the probability that you get bitten is 82%. Now, we're not given a percentage for not bitten, but remember, if these add up to 1, then this should be the remaining 18. Okay, so 0.18. Alright, now most of this description goes into just people being bitten, right? So if you are bitten, you'll either become a zombie, that's 95% of the time, or you'll survive by amputation, that's 0.05%, or sorry, that's just 5% of the time. Right, so if you, so once you're a zombie, that's it. You're no longer considered human, so we're not concerned about what happens after this. Now, if you're amputated, let's say you get bit in the arm, your arm's amputated, well, you're not out of the woods yet. You can die by human hands, and that occurs 95% of the time, or you die by hunger. It's only 3%, that's not so bad. I guess there's lots of SpaghettiOs. So that HG for hunger. Or you die by thirst, which is even smaller, so I guess the water's not contaminated yet. Okay. So those are the outcomes if you get amputated. Great. So let's say you're one of the lucky few that doesn't get bitten. Well, you're also not out of the woods. You have a 45% chance of dying from hunger, 15% chance of dying from thirst, and a 40% chance of dying by human hands. So, even though you don't get bitten and you haven't been amputated, but notice that you die from hunger and thirst it's more likely that you die from hunger or thirst this way. 0.45, thirst 0.15. Right. I don't know why that is. Alright, so let's make sure that everything adds up to 1. Okay, so this adds up to 1. This adds up to 1. 95 plus 0.05, that's 1. Then that's 40, 85. 85 plus 15 is also 1. Alright, good. So this seems likely to occur. And we want to know the probability of dying from thirst. So that means we want to know what is the likelihood we die from thirst after amputation, after being bitten, as well as the probability we die from thirst if we're not bitten. So remember that these are independent events, okay? If you're, well, they're sort of independent events. If you're not bitten, you die from thirst. They both can occur, but one does not influence the other. I feel like amputation is definitely influenced by being bitten, but for the sake of this example, let's just assume that they're independent. Which tells me that we have 2 disjoint paths, either we're bitten or not bitten. Which tells me that we add them together. And we're multiplying these because they're independent events and the intersection of it, right? Dying of thirst is the intersection of these 3 events occurring. Great, so this is 0.18, 0.15, You multiply through, add them up. And what we find is that the probability is 0.0272. Good luck. So at the end of these skeletal notes, which are available in the team drive or class drive, there are 2 other examples that I left here for you to practice things we learned from conditional probability or in independent events, etc. And you should work on them and then come to class with questions. But to summarize, we learned about tree diagrams in this video.
My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. We live in a world of technology. They're collecting information on your humanity. Social networks, gaming, and in-home software.
Hello, Alexa.
Statistics helps us be more aware. Haters gonna hate my spicy lyrics. Why you gotta be so mean? Pulling me towards your extreme moods, but the median never fails to center me. 50 to my left, 50 to my right. Got these correlation and regression tools, forget them fools. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. The mean of the means is the mean. The mean of the means is the mean. The mean of the means is the mean is the mean of the means is the mean is the mean. Be careful not to fall in love. Statistical seduction from above. Your shape so beautifully symmetric to the eye with a single peak so high. I hypothesize and can testify that your p-value is the smallest I've seen. Mix that with a large power and I reach ecstasy. Your residuals defy the rest. A small scale randomized pattern tells me you are the best fit. My name is Llama, and I'm here to teach you stats, skilling you up with the cold hard facts. My confidence is so high, 95%. My margin of error so nil, 110. Can you feel me? Can you feel me? I estimate your population parameter based on only one sampling. Oh, haven't the frequentists told you about me? We live in a world of data, attempting to understand life by statistical strife. The implicit bias of cops, success rate of them jocks, medical advances, and AI romances. Statistics.